Hey everyone, and welcome to today's Explainer. Today, we are exploring the absolute backbone of global communication. We're talking about the TCP/IP internet layer. Whether you're an IT student, maybe prepping for a CCNA or Network Plus exam, or honestly just someone wondering how the internet actually functions on a structural level, you are absolutely in the right place. We're going to unpack exactly how data traverses the planet, moving from your personal device to servers thousands of miles away, literally in a fraction of a second. It's a deeply fascinating system, so let's just get right into it.
Okay, let's dive into this. Here's the journey we're taking today. First, we'll look at the Digital Postal Service. Second, IP addresses explained. Third, packets and routing. Fourth, the ICMP and ARP protocols. And finally, we'll wrap up with a real-world example.
Section 1. The Digital Postal Service, the macro view of global networking.
I want you to think about this for a second. How does a single tap on your smartphone reach a server completely across the globe? When you open up a website, your data doesn't just magically teleport to the other side of the planet. No, it physically travels. It goes from your local modem to your internet service provider, blasts through massive international hubs, and finally hits the destination server. And managing this incredibly complex global journey? Well, that is the primary job of the internet layer. To understand where the internet layer actually fits into the grand scheme of things, let's take a quick look at the standard 4-layer TCP/IP model. Up at the top, layer 4, we've got the application layer. That deals with user services, things like web browsers and emails. Right below that is the transport layer, dealing with app-to-app communication. Then at layer 2, we have our star of the show today, the internet layer. This is the layer responsible for network-to-network routing. And finally, sitting at the bottom is the network access layer, which handles the actual physical transmission of bits over copper cables, fiber optics, or Wi-Fi.
So the absolutely crucial point here is understanding the difference between the transport and internet layers, because they work really closely together. The transport layer, which mostly uses TCP, guarantees the delivery of data. You can think of it like person-to-person communication, making sure the package arrives completely intact. The internet layer, on the other hand, using IP, acts like the Postal Service's massive logistics network. Honestly, it doesn't care what's inside the package at all. Its single, solitary job is figuring out the city-to-city, network-to-network route to actually get that data to its destination.
Let's move on to Section 2. IP addresses explained, the identity of every device.
Now, here's a pretty crazy number for you. 4.3 billion. That is the maximum number of unique addresses that the original addressing system, IPv4, could produce using its 32-bit architecture. Now, back when the internet was first being built, 4.3 billion seemed like an infinite, unreachable amount. But think about today. With smartphones, laptops, smart TVs, and all those smart home devices, we actually ran out of these addresses.
And because of that total exhaustion, we had to upgrade. IPv4 uses a 32-bit system, which looks like those familiar numbers you've probably seen on your home Wi-Fi router, like 192.168.1.1. To fix the shortage, IPv6 was developed. It uses a massive 128-bit addressing architecture. Now, an IPv6 address looks a whole lot more complex. It's got numbers and letters, but it provides so many unique addresses that we will essentially never, ever run out of them. And both of these protocols operate right here at the internet layer.
There is a vital, core technical concept you have to grasp about the Internet Protocol. It is inherently stateless. What does that mean? It means the IP protocol itself doesn't hold, track, or maintain an ongoing connection status. It's not tracking whether the data was successfully received or if it fell into a black hole. It just slaps a destination identity on the data and drops it in the digital mailbox. If a piece of data gets lost, it's actually the job of the higher-level transport layer, like TCP, to realize it's missing and ask for it again.
Section 3. Packets and routing, moving data across the world.
At the internet layer, your data isn't just sent as one giant, clunky file. It gets broken down and encapsulated into tiny units called packets. The basic anatomy of a packet requires three main things. First, the source IP. That's where the data is coming from. Second, the target IP, where the data is going. And third, the payload. This is the actual piece of data, maybe a tiny chunk of a web page or a fraction of a streaming video that is being transported. Whenever your device creates a packet, it usually wants to send it out to the wider internet. But your phone or your laptop, it doesn't have the entire map of the global internet memorized. So it relies heavily on something called a default gateway. The default gateway is simply the specific exit point of your local network. In your house, this is your Wi-Fi router. Your device essentially just hands the packet to the default gateway and says, look, I have no idea how to get this to its final destination, but I know you are my way out. But networks can be messy, right? Sometimes they get confused, and a packet can get lost, just bouncing back and forth between routers endlessly. To prevent these lost packets from literally clogging up the entire global internet, packets have a brilliant built-in safety mechanism called TTL, or time to live. Every single time a packet passes through a router, its TTL value decreases by exactly 1. If that value hits 0 before reaching its destination, the packet is simply discarded. It's a self-destruct mechanism that protects the network from infinite loops.
Let's see how all this builds into a global journey using routing. Imagine you're sitting in Istanbul, requesting data from a server way over in the USA. Step 1. Your device generates the packet. Step 2. It sends it to your home modem. Remember, that's your default gateway. Step 3. Your modem forwards it to your local internet service provider. Step 4. Your ISP reads the target IP address, checks its routing tables, and hands it off to massive international routers. And finally, Step 5. Those routers navigate the packet across the ocean to the specific destination server. And the crazy part? Every single router along the way only looks at that target IP address to make its split-second routing decision.
Section 4. ICMP and ARP protocols, the unsung heroes of the Internet layer.
First up is ICMP, or the Internet Control Message Protocol. If IP is the delivery driver, ICMP is the dispatcher reporting back on the road conditions. It generates error reports and checks network status. Honestly, if you work in IT or a system admin, you use ICMP every single day. It powers the ping command, which sends a tiny ICMP message just to test if a server is reachable and to measure the latency. It also powers traceroute, which is a super cool tool that records the IP address of every single router a packet hops through on its long journey. Then we have ARP. To really understand ARP, imagine a network switch standing up and shouting into a crowded room, "Hey, who has the IP address 192.168.1.1?" And then, a specific router raises its hand and replies, "That's me. Here is my physical MAC address." That is exactly what's happening under the hood on a local network. To formalize that a bit, ARP stands for Address Resolution Protocol. While IP addresses are logical, meaning they can change depending on what network you're currently connected to, hardware itself communicates using permanent, physical 48-bit MAC addresses. ARP operates right there at the boundary of the internet and network access layers. Its whole job is to translate that logical IP address into a physical MAC address so the data can actually be pushed out across the physical cable or through the Wi-Fi frequency.
Finally, Section 5. Real-world example, putting it all together.
And this brilliantly illustrates exactly what happens when you open the YouTube app on your phone to watch a video. First, completely behind the scenes, a DNS service looks up the specific logical IP address for YouTube servers. Second, your phone's internet layer takes your request and creates a data packet, stamping it with your device's source IP and YouTube's target IP. Third, that packet is sent to your default gateway, and routers all over the world read that target IP to instantly determine the fastest path. Finally, Step 4. The packet navigates through ISP networks and massive international hubs until it successfully reaches the YouTube server, which then starts rapidly sending the video packets right back to you.
It is truly a marvel of modern engineering, and it happens entirely behind the scenes, every single day. So I'll leave you with this question. Next time a web page loads instantly on your screen, will you think about the millions of routing decisions and packet hobs that just occurred in mere milliseconds? The internet layer is what makes our globally connected world possible. And while IP gets the data where it needs to go, remember, it relies on the transport layer above it to ensure nothing gets lost in translation. But hey, that is a fascinating topic for another explainer. Thank you so much for joining me today, and keep exploring.